Hi there. Thus far, we've been talking about the Maclaurin series expanded out for complex variables. The last time we had seen the general form of the Maclaurin series, we had seen that we have to take the function at the region of 0, we have to add to it z multiplied by the first derivative at 0, plus z squared times the second derivative divided by 2 factorial, and so on. And we had done this for a certain example. So the question at that point was, how do we know if this series expansion is valid for the function that we have considered? How do we know that this is something real that we are actually doing? So in other words, we need to establish if the series that we have written for some kind of function actually converges. So the way to do it is by using the ratio test. So in general, if we have some kind of function, and if we want to see if that function converges, so we can consider just this exponential function. It goes like that, and we can see that the x-axis is the asymptote. Okay, it's getting closer and closer to 0. We can see that as x gets bigger, this function gets smaller and smaller and smaller until it gets very close to 0. So in general, this is what we would like to see for a function that converges. If we were to write out some kind of expansion, like 1 plus 0.5 plus 0.25 plus 0.125, and carries on like that, eventually this is going to get smaller and smaller and smaller, and it will be on the order of 0.0001 and so on. So it's going to become something very small. So eventually it will reach a point where we're just adding almost 0 to this series. So that means that this series has reached some kind of definitive value or close to some definitive value. And the key characteristic of this is that the next term in the series is smaller than the last. You can see the third term is 0.25 and the second term is 0.5. So each next term is smaller than the one before it. So we can make use of that fact. That is the fact that we use when we are applying the ratio test. We can generalize this a bit more, and we can write a function x as being the sum of some polynomial. So a naught plus the second term is a1 as a function of x plus a2 as a function of x, and so on. And then we would have an to the power of, as a function of x. So when we write the ratio test, we are applying the fact that the next term is smaller than the last. So what we're looking at is the next term. So the general term is an. Any one of these things could be an. So if we're considering the next term, we are saying an plus 1 as a function of x, and we divide that by the term before that, which is an. And if this next term, an plus 1, is actually smaller than the previous term, then it should actually be less than 1. We should actually have a fraction. We can see that if we take 0.25 and we divide it by 0.5, then we actually get 0.5. Okay, let me just write that a bit better. If we take 0.25 and we divide it by 0.5, then we get 0.5, which is less than 1. So we are applying this logic here. So what we're doing is that we're taking the ratio of these terms, we're applying the absolute value, and we're taking the limit as n approaches infinity. When we do that, we would have computed some number, call that L, and when this L is actually less than 1, then we know that the series converges. So this is the key point here. We have to check using this ratio that L is less than 1. So if L is more than 1, then it means that the series diverges. So if L is equal to 1, then we have a situation where the ratio test doesn't actually work, and we have to use some other method to establish if the series converges. So let's just apply that logic to a simple example. We could have the function f of z is equal to sine z. So firstly, we're going to expand this in terms of the Maclaurin series, which we can actually see here on the top. So there's the Maclaurin series. So we have to compute f at 0, the derivatives, and so on, and we put this entire thing together like that. So firstly, we compute f at 0. So let's write it here. So we have f of 0, which is equal to sine of 0, which is just 0. Then we have the first derivative, which we need. Derivative of sine is cos. So we have cos z. Then we compute the first derivative at 0. So we have cos of 0, which is actually equal to 1. Then we compute the second derivative at z, and we see that that is minus sine. Derivative of cos is minus sine. We have minus sine z. Then we compute that second derivative at 0. So minus sine of 0 is just equal to 0 again. Then we compute the third derivative at z. The derivative of minus sine is minus cos. And then we compute the third derivative at 0. So that's minus cos z of 0, which is minus 1. Okay, so if we look at the pattern here, the derivatives are taking on the value of 0 for even numbers, and then we have alternating between 1 and minus 1. So let's write our series expansion, Maclaurin series, for this particular example. So f of z is equal to the first term is f of 0. We can see that that's 0, so we write 0 here. Then the second term is z, and then we have to multiply that by the first derivative, which is 1. And then the third term is z squared. Then we have to multiply that by the second derivative, which is actually 0. Then the third term is minus 1. We have z cubed times minus 1 divided by 3 factorial. And it goes on like that. So if we were to just simplify all of this, what would it look like? We would get f of z is equal to z, that's the first term here. We don't have even numbers, then we can see that the next term is a negative. So we have minus z cubed over 3 factorial. Then we have plus z to the power 5. Remember that even numbers are 0, being multiplied by 0, divided by 5 factorial. And we have minus z to the power 7 divided by 7 factorial, and so on. So if we wanted to have a general term for this kind of expression in terms of n, then what it would be is minus 1 to the power n multiplied by z to the power 2n plus 1. Okay, so that's 2n plus 1. So whenever we want to compute an odd number, then we would just say 2n plus 1. For example, if we take n is equal to 2, you'll get 2 times 2, which is 4. 4 plus 1 is 5. So that is z to the power 5. And then minus 1 to the power n. So n was equal to 2. So minus 1 to the power 2 is plus. We can see we have the plus here in front. And then we just have to divide by that 5 factorial. So the way we'll write it is, same way we want the odd number. So it's 2n plus 1 factorial. So now we are in a position to apply this ratio test. So there's the ratio test here, and that's what we're going to use. So this L was equal to the limit as n approaches 0, sorry, n approaches infinity, of firstly a n plus 1 divided by a n, and we take the absolute value. So if we were to write it now for this term, so we have a n, so this is what a n is equal to. So this is the term that we are dividing by. We're going to divide by this term, and the numerator is a n plus 1. So we're going to take the same thing, and wherever we see n, we're going to substitute it with n plus 1. So let's look at the numerator. So we have now minus 1, and then we have n plus 1, then we have z, then 2n plus 1. So that will be 2 into n plus 1, then plus 1, and then divided by, now this 2 into n plus 1 plus 1. So this plus 1 here is the one that we have to write here. And this whole thing is factorial. So that was only the numerator, okay? That was only the numerator. We now have to divide by this an. So that is minus 1 to the power n, z to the power 2n plus 1 divided by 2n plus 1 factorial. We now have to simplify this. We take the limit as n approaches infinity, and we write it out. Okay, we can simplify a lot of these things. So we have minus 1 to the power n plus 1. We have minus 1 to the power n plus 1. So we use our laws of exponents. This n is going to go to the numerator here, and we have to subtract it out. So we have 2 minus n. Then we have z to the power 2n. Then we have 2 times 1, which is 2. 2 plus 1 is 3. So we have 2n plus 3. And then here we have 2n plus 1 in the denominator. So we take that to the top and we change the sign. So it's going to be minus 2n minus 1. And we take this entire term with a factorial to the top as well. So we have 2n plus 1 factorial. So now what's left? What's left is this term. So what it is 2n, then 2 times 1 is 2, then 2 plus 1 is 3. So we have 2n plus 3 factorial. Okay, but remember now what is factorial. For example, if we have 5 factorial, that is just 5 times 4 times 3 times 2. So we minus 1 each time. So that's what we're going to do here. So this 2n plus 3 is the same thing as writing 2n plus 3, then we minus 1. So we have 2n plus 2. Then we have 2n plus 1. And we can keep multiplying that out. So beyond this point here, so beyond that point, we can just simplify that whatever is going to come afterward as factorial at that point. Okay. So what we have essentially said is, for example, 5 times 4 times 3 times 2, etc. So we can simply just say that this is 5 times 4 factorial. That's what we've essentially done. What that means is that this term cancels out with that. And also what we're left with here, we're left with minus 1 to the power 1, which is just meaningless because remember we're taking the absolute value here. And then we have 2n minus 2n cancel out, and then 3 minus 2 is 1. Sorry, 3 minus 1 is 2. So we have z squared, 3 minus 1, giving us the 2. And in the denominator, we have 2n plus 3 and 2n plus 2. And we're taking the limit of this as n approaches infinity. So what we're saying that in the denominator, we have a number that gets very large. If we divide something by something that's getting very large, then what it becomes is 0. So this limit gives us 0. And what do we see? We see that 0 is less than 1. So what was our criteria? Our criteria was that when we compute this ratio, we should get that it should be less than 1 for it to converge. And of course, we can see that 0 is less than 1. So it means that there's no limitation on what value of z that this can apply to. It means that this expansion that we've done is actually valid for all values of z. It will converge. So in a nutshell, when we are applying a series expansion to some kind of function, we compute this ratio and we check for values of z for which this ratio is less than 1, and that will tell us if this series converges and whether we're able to use it. So thank you very much for watching. In the next upcoming videos, we're going to talk about applying this to the radius of convergence. We're going to look at other functions, and then after that, we'll start applying it to the Taylor series, the Lorentz series, and we're going to look at residues and also how to calculate zeros and poles.